Okay, welcome again. My name is Larry Baker. I'm a research professor in the Department of Bioproducts and Biosystems Engineering. This is the second of lectures in our module on biophysical considerations for water resilience. And this is one of about 8 modules in our water-related training, education, and research in the Global South education videos. And today I'm going to be talking about water contaminants. Our audience is largely social scientists, humanities folks and such, quite possibly with very little science background or relatively limited knowledge of water contaminants. So the idea here is simply to introduce the idea of water contaminants and which ones are most prevalent in various parts of the globe and how they become water, these contaminants become contaminants. 2 pictures here. I'll talk about both of these later on. This is a situation in a city in Mexico, in Cuernavaca. Shows a very typical situation in the Global South where you have maybe a wetter area of the Global South. There is flush toilets in these houses, and they have pipes coming out the backs. It's a little hard to see, but these pipes kind of wind around the sidewalk here, goes down into a gorge, and discharges the sewage directly, untreated, into a stream. A very, very common situation in much of the Global South. The slide on the left is a copper mine. These are quite large. They can be several miles across in terms of impacted area. Often there's water involved in the processing and such, and very commonly create some level of contamination. At the very best, some contamination. At the very worst, very toxic contamination. Most people in the globe are living in living in cities now. We just crossed the 50% line in, I believe, 2007. In the future, there is going to be a great deal of growth in cities, particularly in the Global South along here. This is the same slide I showed in the previous. I will be showing in the next lecture. A great deal of growth. Great deal of potential for water problems. So, what do we have in terms of types of contamination? First, we have biological disease. Some bacterial examples are typhoid, cholera, and many others. Protozoans, things like Giardia and Schistosomiasis. And most of these are diarrheal diseases. They cause diarrhea. And sometimes, particularly for cholera, it's the diarrhea alone that kills a child or a young person. You die by dehydration, by not having clean water to drink during the disease, by not having antibiotics that maybe can treat the disease, and so forth. This is a number from the World Health Organization of 2 million people per year. This is mostly the very young and the very old are people who die here. They're often from fecal sources. So we'll talk about fecal contamination in just a moment. And then we have chemically induced disease, things like arsenic, lead, and nitrate, which may be natural, many times are natural, but they may also be anthropogenic, formed from pollution and such. This is a diagram illustrating how bacteria are transmitted. Here's human excretion. It might go directly into waterborne sewage if there's particularly if there's flush toilets but no sewage treatment. That might go into surface water. That might go directly to humans, or it might go into the food in some way during processing or such and come back to humans. So we have multiple pathways here, and we sometimes talk about multiple barriers. You know, food sanitation being here, water treatment being right about here, sewage treatment being right about here, containment of human excreta, and so forth. But it's a whole system. It's not one thing that can completely prevent diarrheal disease. It's a system of things. The target for death by diarrheal disease, a realistic target for developed countries, is 0. In the United States, in a typical year, and we have a Centers for Disease Control that watches this very carefully, on the average, the typical number is 0. Every once in a while, there's an outbreak, but it's very, very uncommon. So when we think about, I'll show you some numbers later of different continents and stuff, and hundreds of thousands of children per year. Think that the goal here, the realistic goal with development is 0. The second of the pollutants is nitrate. This causes a disease called methemoglobinemia, or blue baby syndrome. It makes it hard for babies. The nitrate ties up with the hemoglobin, makes it hard for babies to get oxygen. It's called blue baby syndrome because it mainly affects very young children. The World Health Organization has a limit, 45 milligrams of nitrate per liter. In the U.S., we put that in terms of nitrogen, so it's about 10 milligrams of nitrate nitrogen per liter. This occurs from several sources. Leaching of nitrogen fertilizers in agricultural areas. I'll talk about that in a minute. Or in urban areas, particularly in the global south, there are pit latrines. There might be highly contaminated surface water in the first place, animal manures, leaky sewers, and such. And I was a bit surprised to discover a few years ago that there are very elevated nitrate levels in African cities. Typically, in the U.S., we don't see elevated nitrate levels in urban areas. We see them in agricultural areas. But certainly in the global south, you see high nitrate levels. If there's animals, if there's pit latrines, there's likely to be high nitrate in the groundwater. And it can, in some circumstances, nitrate can be from natural sources, but that's less common. Okay, a little bit more on nitrate in agriculture. How do we get high nitrate groundwater? We have high inputs of nitrogen to crops. This can be either fertilizer or manure, but generally beyond the needs of the crop. It's hard to get what we call high nitrate use efficiency because as conditions change, the crop uptake of nitrogen changes, and there's a really strong tendency to over-apply nitrogen if it's relatively inexpensive. In parts of China, for example, nitrate levels in groundwater can reach 300 milligrams per liter. Remember before we were talking 45 as being a limit. This occurs more where you have shallow groundwater, less distance to travel, and where you have sandy or coarse textured soil. So the nitrate moves very easily through soil and goes down into groundwater. It doesn't get impeded very much once it moves past the root zone. If there's drainage water, and this is a case here of drain tiles going under this field and coming out right here. You can see the water coming into a ditch. Again, high nitrogen inputs, and in this case, drain tileage that just really moves the groundwater into a drainage ditch and then flows downstream. With arsenic, I would say most of the time throughout the world it's naturally occurring. It can occur from mining, but there are many, many places where arsenic is natural. Parts of the western United States, I actually studied it right here, but certainly Bangladesh, many parts of the world, arsenic is prevalent in groundwater. 100 million people are exposed to high levels in drinking water. There is a search for low treatment technology. I'm going to refer you to a web page at Berkeley. There are fairly inexpensive ways of removing nitrate from well water and such. But it causes cancer and kind of a skin roughening. But of course, the thing that's really dangerous is cancer at the level of 50 micrograms per liter, which is the US standard. I believe that's also the global standard. You have about a 1 in 1,000 chance of getting cancer if you've been drinking water at that level, at 50 micrograms per liter for your entire life. And then salt, say the curse of civilization, perhaps the only pollutant that's actually done in civilizations. It occurs by at least 3 mechanisms. Seawater intrusion, when you have a freshwater aquifer very near a coastal area and you draw the groundwater down, the salt water just kind of comes pouring into it and contaminates your well. This is very common. It occurs in cities from Miami, Florida to the Gaza Strip and probably everywhere in between. And it can ruin your water supply completely if it goes on long enough. Salt in source water, I'll refresh your memory about that in just a bit, or expand on what we talked about in the last lecture. And salts are added to municipal sewage, just the natural course of using detergents, and water treatment itself adds some salts. Human excretion adds some salt. And that can be enough to make reuse of the water, to make it so you can't necessarily reuse that water for irrigation and stuff in some circumstances. This is similar to the slide I showed you before with evaporation and such going on. But here we're going to put, in this hypothetical example, salt. The salt concentration in irrigation water is going to be 500 milligrams per liter. Salt is the same thing as total dissolved solids, or what I'm calling down here, TDS. Exactly the same thing as salt. 75% of the water is evaporated, same amount as I talked about in the previous slide. And now the water that's evaporated has zero salt that goes up in the air. All the salt goes downward. So now we have 25% as much water with 4 times as much salt. Now you're at 2,000. When you were at 500, you could grow tomatoes, carrots, salt-sensitive crops fairly well. If you were to reuse this water, bring it back up, pump it back up and irrigate a field over here with tomatoes, you would really have trouble. And if you go through that cycle several times, you can get concentrations up in the 3,000, 4,000 milligram per liter level. You really have a hard time growing much of anything after a while. So this is a very, very common situation everywhere in the world where people are irrigating. There are also natural saline groundwater systems. Much of the world, northern Canada, many parts of Africa, Western Australia, parts of India, parts of Russia, and so forth. So we have some natural saline groundwater also. Some other contaminants, mine waste, copper mine, gold mining, lead, zinc. It depends on what mineral is being mined, but typically many of these are associated with sulfide materials, and it's the sulfide oxidation during the processing that makes the water acidic, and then it transmits metals downstream. Hoping Hilary Waters, who's now in Zambia, will provide a lecture on this later more. Okay, we better cut that right there. Oh gosh, I should have known better. Okay, can we just cut and start over?
Sure.
On this slide? Okay. Other major contaminants in drinking water, here are a few examples. Mine waste, it depends what kind of mineral is being mined, but some of the more common leachates from this process are copper, lead, zinc, and arsenic. And if not very carefully controlled, these can be at very high concentrations in streams and groundwater near mine systems. Pesticides, mostly from agriculture. These can be quite toxic. The impacts are sometimes not terribly well known because we tend to use many pesticides in a given setting, but there's certainly many that are quite toxic. Acids and bases, sometimes we acidify water for industrial purposes. Sometimes we add bases to raise the pH. And there's so many ways we do that, it's hard to say. It's actually when acids and bases go into a stream, they typically get neutralized downstream, but for a while they can be real problems. And acids particularly can be characteristic of mine waste. You can have extremely acidic systems. For example, with coal mining, you can have streams down, the pH of streams downstream from a coal mine can sometimes go below 4, sometimes into the 3s, as acidic as vinegar. And lead in drinking water, mainly leached from pipes, not so much from natural sources. But you have lead solder, or in some cases in older areas, you have lead pipes. And if the water being treated and going into a pipe isn't very carefully controlled with respect to pH and such, it can be corrosive and then corrodes the lead out of the pipes. This is the problem we had in Flint, Michigan, for those of you who I've heard about that. In summary, most of the world does not have safe drinking water. The most common water contaminants are pathogens of various types. This again is completely controllable as countries develop. Pathogens infect by multiple routes, and you've got to hit all of them, and particularly through the fecal route. It starts with a sick person who then exposes other through the fecal route. Many widespread chemical contaminants, or some are nitrate, arsenic, salt, and many other more localized contaminants include mine waste, a good number of metals, lead, acids, bases, and pesticides. And in one of the next lectures, I'll talk about ways to treat water and wastewater to make it safer. Thank you.